Alright, so in this particular video we have a 10 kilogram box that's pushed along a rough horizontal surface by a constant horizontal force F. As shown below, at time t is equal to 0, the velocity of the box is 6 meters per second in the same direction as the force. And it says the box reaches a velocity of 30 meters per second after a distance of 80 meters. The coefficient of sliding friction between the box and the surface is 0.2. So here's the diagram to help you visualize things. Here is a force F pushing this particular 10 kilogram box to the right. It has an initial velocity of 6 meters per second to the right, and then it's going to accelerate, in this case speed up to a velocity of 30 meters per second to the right. Okay, so here at the bottom it says the position at time equal to 0 is equal to 0 meters, which is, it's just fancy for saying the initial position is 0 meters per, which is 0 meters. And then here the coefficient of kinetic friction between the box and the surface is 0.2, and the final position here is 80 meters, which is essentially what is stated in the wording. Alright, so here's A, B, C, D, and E. If you need to, pause the video and write these parts down and keep up. Let's do part A and B. Part A asks you to find the acceleration in the box. The easiest way to find acceleration in the box is to use this particular kinematics equation. So if you actually pause the video and look at the diagram properly, I noticed that Vf is given, Vi is given, and the displacement is given. It starts at 0, it ends at 80 meters. So therefore, to find A, I would use this function because all these information are given to me. Okay. In order to solve for A, I need to get rid of the 2 and the delta x by dividing both sides by 2 and delta x at the same time, which means Vf squared minus Vi squared is all over 2 delta x. I know Vf is 30, I know Vi is 6, I know delta x is 60, so I'm just going to plug those in. So you'd be 30 square minus 6 square times 2, divided by 2 times 80. So the work on the screen here. Alright, so if you simplify the numerator correctly, it would be 900, because 30 squared is 900 minus 36, which leaves you with a difference of 864. And then 2 times 80 in the denominator is 160. And if you do that on your calculator, you should get a value of 5.4 meters per second squared. Here, I've decided to include the direction for you because the problem asks you to find the acceleration. In this case, the force is pushing the system to the right, which implies that it is accelerating to the right, which means acceleration is positive. So I do need to include the direction there because it is a vector quantity. Part B, to do part A using a different strategy. Okay, just in case your brain takes you here where you did average acceleration is equal to change in velocity over change in time, which is fine. You can break up delta V into Vf minus Vi over change in time. What you hopefully recognize by now is that Vf and Vi are given in the diagram. Vf is 30, Vi is 6. What you are not given is the amount of time that it took for the box to cover this 80 meters. You were given everything, well, you were given a lot of information except for time, which means this is a quantity that you don't know, okay? You don't know what time is, but that's okay. That would just indicate or suggest that you need to use a kinematics equation to find time. So in order to find time for this particular problem, I would use the average velocity functions, okay? Average velocity by definition is displacement over time. Under constant acceleration, which this is assumed to be, I can find the average velocity also using Vi plus Vf divided by 2. Because those two functions are equal to each other, I can set them equal to each other here. So this statement here is valid. However, what I need to find is change in time. But as you notice here, change in time is in the denominator. So algebraically speaking, you have to manipulate the function to get delta t in the numerator. I think the easiest way to do is just to flip the function upside down. Okay, I need to flip the left side and the right side upside down in order to get delta t to the top. However, doing so just gets delta t to the top. But what I notice here, I notice that delta x is in the denominator. Well, to get rid of this delta x in the denominator on the left side of the equal sign, I would just have to multiply both sides by delta x, or I would just move the delta x up over here. So therefore, I have 2 over Vi plus Vf in parentheses times delta x. Well, I know what Vi is, I know what Vf is, I know what delta x is. So therefore, Vi is 6, Vf is 30, delta x is 80. And if you punch out in your calculator, you should get a time value of about 4.4444 seconds running. I round off to 2 decimals here, okay? Therefore, you just found what delta t is. Now you can just plug that value in for t. So t is equal to 4.44. So if you do that, you'll get 30 minus 6, which is 24. And then 24 divided by 4.44 seconds is also the same value that we got using the strategy on the right side of the board or the screen here. Okay, so therefore, I encourage you as you practice, see what the easiest way and quickest way to get to your outcome rather than going around. However, if you did this strategy on the screen here, where you found average acceleration by using change in velocity over change in time, you were forced to find the time that it took to cover the first 80 meters. So if you recognize Part B asks you to calculate the time required to travel the 80 meters. Well, you just found what it was. Okay, so the answer for Part B is simply 4.44 seconds. So sometimes, depending on the strategy you exercise, you might find answers to different parts, based on how you think of these problems. Again, so by accident, you found the answer to Part B had you taken this approach. Okay, so the answer to Part B once again is 4.44 seconds. Let's do C, D, and E. Part D asks us to find the kinetic frictional force F of K acting on the box. Well, the easiest way to find F of K is using this particular function. I'm going to use this because the coefficient of friction is given to me. Mu K here is given as 0.2. So that's an indicator to use this particular function to find F of K. Maybe not all the time, but it's a good starting point. So F of K is equal to the coefficient of kinetic friction times the normal force acting on the box. Well, we can find what the normal force is simply by drawing our free body diagram out. Here's the box. The blue arrow that just popped up on the screen, that is your F of G. The weight of the box is going to be directed downward, okay, onto the surface, hence pushing down on the surface. So F of G is just mass times gravity, or acceleration due to gravity at the surface of the planet. However, because the box is pushing down onto the surface, but Newton's third law suggests that there is a counter contact force. And that contact force in this unit is called normal force, F sub n. We do know for this particular problem, so it's not all the time, but for this particular problem, there are no additional vertical forces, so therefore, we know that the magnitude of these two blue arrows must be the same. So we can say that F of n has the same magnitude as F of g because it does not accelerate upward. So the box is to remain on the horizontal surface, which implies that it's not flying upward, nor is it sinking through the surface. Therefore, that statement has to be true. Fn must equal to F of g, vice versa. So therefore, I can do that quick substitution. Wherever Fn is, I can say Fn is equal to the magnitude of F of g. Well, I know what F of g is. F of g, I can break it up into mass times gravity. Well, by doing so, I know all my values. I know mu k is 0.2. I know the mass is 10. I know gravity due to acceleration at the surface of Earth is negative 9.8. Okay? And if you simplify on your calculator, you should get a negative value 19.6, which makes sense. In this particular problem, the box is being pushed to the right. So I know the kinetic frictional force, F of K, must be opposing that. So opposite of right is left, and left in this case would be negative. So I know my answer is reasonable. Okay? So therefore, I'm just going to go ahead and highlight that, negative 19.6 Newton. Part D asks you to find the magnitude of the applied force. It tells us that the box is being pushed by a force, but this force was not given to us. Okay? So a common mistake that kids might make is you let the diagram play you. Okay, you get fooled. While there's only one arrow drawn for you for the force, you have to recognize that it's being pushed across a rough surface. So you have to learn how to draw vectors for yourself, just because sometimes it's not drawn for you. So in this case, you have to recognize, because it is being pushed across a surface, a rough surface, there has to be a kinetic frictional force. So you have to draw these vectors out for yourself when one is not drawn for you. I'm going to call this F of K. F of K in this case, again, points left because the box is moving to the right. F of K is trying to slow it down or impedes its motion. So it has to be negative in this one. So therefore, I can break up sigma F into F minus Fk. Okay? Again, sometimes kids just put F equals ma, and that's a big mistake. You need to draw this F of K out if the coefficient of friction is given to you. It's like a ding, 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 there's an F of K, because if there's a mu K, there has to be an F of K. So therefore, To solve for f here in this function, I need to manipulate the function to get f by itself. To get f by itself, I need to move this negative fk to the right side, which makes it positive. And here I know my values. I know m is 10, I know a is 5.4, and I know f of k, okay, is 19.6. I do want to point this out though. I plugged in 19.6 for f of k because earlier in the second line, I'm already telling you that f of k is negative. So here you can add a negative or you can just subtract a positive. Okay, I want to say it again. Here the sigma notation tells you to add. You can add a negative or you can just subtract a positive. So I like to just go ahead and introduce my negative sign by just subtracting this quantity, the magnitude. So I'm already telling you that fk is negative. So when you get down to here, you can plug in just 19.6. If you plug in negative 19.6, you're saying that it's negative twice, which is improper. Okay, so pay attention to your signs. Therefore, if you do this correctly, the value for f is going to come out to be 73.6 newtons, and it says magnitude, so I don't need a direction. So if you need to, listen to that part again. This is where mistake can happen. Sometimes kids plug in negative 19.6 newton when it should be a positive because the negative sign is already accounted for you. Alright, let's do part E. Part E asks if the mass of the block is increased, how would it affect the acceleration? Well, this is pretty straightforward. The function that I just carry over, watch where I'm circling. In the work for part D, I know that f minus fk is equal to ma, so I can just start with that. F minus fk is equal to ma, but it's looking at acceleration, so I need to isolate for acceleration. To get acceleration by itself, I need to divide both sides by m. Okay, so that's just an algebra move there. So therefore, we say f minus fk divided by m would give you a. What you do notice, hopefully by now, is that f of k, this function here, can be substituted for f of k. So we can say that f of k is mu k times mg for this particular problem. And it sits over a denominator of m. So I'm just going to speak slow here and hopefully you keep up. M is in the denominator, but m is also in the second term. So hypothetically speaking, if m goes up, so if this value m goes up, watch what I'm circling. This whole term goes up. Mu k times m times g has to go up because you're multiplying. So if m increases, this term that I'm circling, mu k times mg also has to increase. Well, if f stays the same and you're subtracting by a bigger number, the numerator gets smaller. Well, if the numerator gets smaller, but m gets bigger, so you have less on top and you dividing by a bigger number, in my world that would imply that the value keeps getting smaller and smaller. Okay, so for example, if you have less and less money, but you keep dividing by more relatives, okay, because they keep coming and ask you money, you would give everybody less money, okay, because you have less money now in the numerator, but you keep having more people come. Well, you have less money, and if more people come, each person gets even less, which is, a common sense thing. All right, so other than that, my conclusion is going to be acceleration decreases because the term in the numerator gets bigger here with the m, which implies that the whole numerator gets smaller. But if the numerator gets smaller and you're dividing by a bigger mass on the bottom, it suggests that a is going to decrease. And that's all for this particular problem. All right, I hope that helps. Stay nerdy, don't be whack.